Hello and welcome. In this video I'm going to deal with resistor networks. In resistor networks there are three physical quantities that we are always required to calculate: current, voltage and resistance. You could calculate any one of these from rules that concerns the various circuits. What I mean is this: when you look at a series connection of resistors, there are three formulas which pertains to current, resistance and voltage. You could use any one of those equations. Similarly, when you look at a parallel connection of resistors, there are rules or laws or formulas which pertains to voltage, resistance and current. For instance, in this particular circuit, we are required to calculate the effective resistance in the circuit, that is the total resistance in the circuit. How do I use the rules which are provided? If I'm asked to calculate total resistance, I could get that one by dividing total voltage by total current. That is one way of calculating that, or getting this. Let's find out what is provided. I've been provided with the total voltage, but the total current is not provided. In fact, it is asked for somewhere around here. So I abandon that route. It may not be the best route to follow. The next route is to try now and combine the various resistances that are provided in this particular circuit. That is the option that I have. When I look at this circuit, it is not a straightforward circuit. What I mean is this: it is not a purely parallel circuit or a purely series circuit. It is a combination of series and parallel connection of resistors, and this is where problem begin. This is the first step that you need to undertake when you are carrying out this kind of calculation. Look at the circuit carefully and identify those two or three resistors that you can be able to combine it together directly in order to get some kind of total resistance for that connection. What I mean is this: in this particular circuit, when I look at the resistor R2 and R1, they are in parallel, but I cannot be able to get the effective resistance for R1 and R2 directly just because they are in parallel by using the equation product over sum, or by using the inverse of the resistances. Why is that? It's because there is this complicated circuit here which is also a parallel connection of resistors. You find that this parallel connection of resistors is found within a larger parallel connection of resistors which is connected in series with R5. It's more like R3 and R4, which are in parallel and nested in another parallel connection of resistors. And this is where most students usually find a problem. They are unable to know where to start when they are confronted with this kind of network. This will be my method or the advice that I can give you. Identify that small unit which you can be able to get its effective resistance without it affecting or being affected by some other resistors. In this case, when I look at R3 and R4 and I look at the current which moves into that connection somewhere around here, it splits at this point in this direction and in this direction. So R3 and R4 are in parallel, and you find that I can be able to get one resistor which can represent these two. If they are in parallel, then I can do product over sum. I can multiply 2 times 3 divide by the sum, 2 plus 3, and I get 1.2 ohms. So there is a single resistor which is going to represent these two. So in the next slide, I've duplicated this slide so that I can go to this slide here, and now I'm going to remove these two resistors, this one and this one, so that I can have just one resistor representing these two. So I'm going to have just one resistor whose value is 1.2 ohms, and I complete that section there. You can see I've been able to calculate the effective resistance for the two resistors without its value being affected by this or any other resistor in the circuit. So identify that very small unit within the network where you can be able to get its effective resistance without it being affected by other resistances. Now let's look at now what I've got here. So remember, this represents R3 and R4. This one here, R3 and R4, they were in parallel, and the effective resistance is 1.2 ohms. Now when I look at R2 and this 1.2 ohm resistor, I can see that they are in series, because when this current flows, the current which flows through R2 is the same amount of current which flows through this single resistor. Of course, when I go back to these two resistors here in the previous circuit, I find that this current is split to give this and this one here. So this current here is the current that I'm talking about here. It is this one. Remember, this current is going to split into two so that there is some current through R3 and R4. But if R3 and R4 are represented by one resistor whose value is 1.2 ohms, then it follows that the current through that parallel connection is equal to the current through R2. The two are in series. Since they are in series, I can just directly combine R2 and 1.2 ohm resistor to get one resistor which will represent this and that. That is when now I get 1.2 ohms plus 4 ohm resistor, and I get 5.2 ohms. So in the next one, I'm going to remove this resistor, the 4 ohm resistor, remove it, so that now I have one single resistor of 5.2 ohms connected here. 5.2 ohms. You can see that I'm reducing the complicated network slowly into a simpler circuit. At this point, I'm able to see that the 5.2 ohm resistor that I've just obtained is connected in parallel with R1, and in order to get total resistance there, I do the product, which is 5.2 multiplied by 1, which is just 5.2, and 5.2 I add 1, where I get 6.2. So over here I've got 5.2 divided by 0.84 ohms. It is 0.8387. I round it to 0.84 ohms. Okay, let's continue. Now I've got one resistor which will represent these two. So let me duplicate this circuit there, so that now I can get one resistor whose value is 0.84 representing these two. So I'm going to remove this. This single resistor, which is now here, will have a value of 0.84 ohms. And you can see now the 0.84 ohms is in series with a 5 ohm resistor here, and if I add the two, I get 5.84 ohms as my total resistance. And you can see how easy it is when I continuously reduce a complicated circuit into a purely series connection of resistors. Or if I move back here, I can reduce this complicated circuit into, I can reduce that section into a purely series, and then I reduce this circuit into, this section here is purely parallel, and then finally I have a purely series connection of resistors. Very important. So let's calculate the current through R5. Current through R5, it is the current through the 5 ohm resistor, so that current will be flowing this way, and it is the same current which flows back to the battery, so it happens to be equal to IT. One way of working IT is to get the total voltage, which is 6 volts, divided by the total resistance, which I've got as 5.84. So I have a 6, I divide by 5.84, and I have 1.027 amperes. 1.027 amperes. And then the next part is to get the voltage across R3. If we move back to the circuit that we had over here, I need voltage across the 2 ohm resistor. The voltage across the 2 ohm resistor, there are two ways of working it out. If I know the current through the 2 ohm resistor, I can multiply it by 2 ohms to get that voltage directly. What I'm saying is I can use Ohm's law, which is V is equals to IR. But the problem here is I do not know this current. Although I know the resistance, I do not know the current. So I abandon that process. I have to look for a different method. Now when I look at this kind of circuit here, if I can be able to get the voltage across this combination of the two resistors, R3 and R, if I succeed in getting this voltage across this combination here, I will have got the voltage across this one here. So to get this voltage here, it is similar to getting the voltage across the combination of the two resistors. They are the same, because I have to remember that the voltage across this combination here, this resistor, is equal to the voltage across this resistor, is equal to the total voltage across a single resistor whose value is 1.2. Let's see whether that one is possible. When I look at the next, when I combine this one and this one, I get this simple connection of resistors, and finally I get this. Now I know the voltage across this one here, or rather I know the total current which flows here. So what I can do at this point is to calculate the voltage across R5. The voltage across R5. The voltage across R5, which can be written as VR5, And why am I calculating that? I'm calculating that so that when I subtract it from the 6 volts, I will get the voltage across this. Let's just proceed and you will see what it amounts to. So I get the total current, or the current through that R5, times the voltage itself, 5 volts. So I get 5 times 1.027. I have 5.135. Volts. That means the voltage across this connection here, the voltage across the 0.84 ohm resistor is 6 minus this value. Again, I'm using a very simple rule here, that total voltage in a series connection of resistors is equals to the sum of the individual resistors. So if I know one of them, I can calculate the other one by subtracting it from the total voltage. So remember, Vt is equals to V1 plus V2. So if I know V2, I can work out V1 by doing V2 is equals to Vt minus V1. That is what I'm doing here. So I'm going to get 6 minus the answer over there. I'm going to get 0.865. 0.865 volts. Now, if I work backwards, the 0.865 is equal to the voltage across the 1 ohm resistor here. It is also equal to, so the voltage across this is 0.165. It is also equal to the voltage across here. This voltage was 0.8. Sorry for that. I've just lost it. 0.865. So over here, this 0.865 volts, like that. That is 0.865 volts is the same voltage across the total of this connection here, from here to here. This voltage here is 0.865 volts. I hope I've written the correct value. 865, yes, that voltage, 0.865 volts. So that means that the V2 plus V across this connection is equal to this much. So if I want to get the voltage across this one here, I can do something very simple that we have always learned, that if I have two resistors in series, R1 and R2, they are in series, R1, R2. I can get V1 by getting the ratio of R1 to the total resistance, R1 plus R2, times the total voltage, V1 plus V2. Let's see how this one works out here. If I want the voltage across the 1.2 ohm resistor, I want the voltage across this, I'm going to treat it like V1 is equals to R1, whose value is 1.2, and here I've got 1.2 plus 4, I get 5.2. That is R1 plus R2, R1 plus R2. And what is the value of VT? The whole of this, 0.865. 0.865. And that will give me, so 0.865 times 1.2 divide by 5.2 and I get 0.1996. 0.1996 volts, which is approximately equal to 0.2 volts. Have I answered the question? What have I been asked? I wanted VR3. Let's see where VR3 is. VR3 is here. And we had said, we had reduced that circuit, combined R3 and R4 to give me this one here. And we have already agreed that the voltage across the 1.2 ohm resistor is equal to the voltage across the individual resistors which formed that parallel connection. So over here, what I got here as 0.2 volts, that is previously, let me just go back to it. Where is it? Here. What I got here as the voltage across the 1.2 ohm resistor is equivalent to the voltage across R3 and is equal to the voltage across R4. So, to answer that question, VR3 is 0.2 volts. Very simple. Lastly, I want the current through R1. Where is R1? R1 is the 1 ohm resistor. In order to get the current through R1, I can decide to divide the voltage across it, which is 0.865 volts, divided by the resistance itself, which is 1, and I get 0.865 amperes. That is how I would work out this question. Remember what we started with. Let me go to a blank question. This is what we started with. Given a complicated network of resistors, and like I pointed out, I've marked many scripts, and the students usually have a problem with this type of circuit. And the ones who get it correct, they always get it by trial and error method. We want to get a clear-cut method that you can always use. The first is to remember Ohm's law. V is equal to IR. Just remember V is equal to IR. And know that in a network of resistors, these are the physical quantities which you were asked. You are either asked to calculate a voltage, the current, or some kind of resistance somewhere. There are always two methods of calculating any one of these physical quantities given. For example, if it is a series connection of resistors and you're asked to calculate VT, for example, you can use IT times RT. So it depends on what is provided. If you are provided with IT and RT, you can work out VT. If none of those is provided, then you've got to go to another method of saying VT is equals to V1 plus V2 and see whether it's possible to work out anything from that. So there are always two methods. In this case, we wanted the effective resistance. So in order to calculate the effective resistance, there are two methods. The first one is to divide VT by IT. Although we know VT, IT was a problem. We didn't know it. So we abandoned this method and we went to the second method, which requires us to combine the various resistors that we have in the circuit. We could not use directly this method, RT is equals to R1 plus R2 plus R3 the equation for series connection of resistors directly for the whole circuit. Why? All these resistors, some are connected in series, some are connected in parallel. So it's not possible for us to use this equation directly. Neither is it possible to use this other equation directly, because like I said, this one is a combination of series and parallel. So to use one particular equation for a pure series connection of resistors or an equation for a series connection of resistors was not possible. So we have got to work it out in bits. So the next question was, where do we start from? Now, this is, if you've been following the discussion, this is where you start from. You always identify those 2 or 3 resistors or even 4 resistors whereby you can use this equation or this equation directly. When I look at the whole of this circuit, there is no one point where I can use, at this particular moment, where I can use this equation directly. But there is a point where I can use this equation directly, because when I look at R3 and R4, they are in parallel. So I can combine 2 and 3 and get one single resistor which represents the 2 of them without that value being affected by the 4 ohm resistor or the 1 ohm resistor or even the 5 ohm resistance here. It's always important that when you identify that smaller unit in the circuit, you ask yourself, if I use this equation on that equation, will it be affected by the other 2 resistors at that particular moment? For this case, we found that it wasn't, because we were able to combine this and this to get one resistor which represents R3 and R4 directly. And then the rest of it just flows. We found that now we can combine this one and we get the next resistance directly without this one affecting it. Then next we combine this and we got the one resistor which represents those 2, and so forth. That is the method that we always use. Then when it comes to that is the method that we used for effective resistance. When it comes to other physical quantities which have been asked in the question, the voltage and the current, we've got to be ready again to use the Ohm's law, V is equals to IR. At the same time, remember what happens to the voltages and the currents and the resistances in the various connections of resistors. In other words, when I went to question number 2 here, I'm asked to calculate the current through R5. I had to ask myself, there are 2 methods of calculating current. Is it possible for me to use the simplest one, which is VT over RT? I realized that in the previous part, I had just been asked to calculate RT, and I know VT from the circuit. So that one was a direct method, and it wasn't difficult. But when it came to R3, I had to think about R3 to calculate VR3, that's the voltage across R3. I had to think about several methods. So hopefully you can go through this video several times and then do some practice on other networks of resistors in order to clarify that aspect. I hope I've been of help to you, and that network of resistors will no longer be a problem as far as these forms of calculations is concerned.